Okay, so now we're going to consider the case with information asymmetry and then try to formulate and solve this problem. Sometime we will need to use this revelation principle to help us simplify the problem. So now we're pricing under information asymmetry. The valuation is hidden and the first best pricing plan will not work, right? Because now you are not able to make an offer according to his type. It's impossible to do that because you cannot see what's his type. So how about the following? I may collect the two first best contract and make it a plan or a menu, okay? A menu of two contract for the consumer to select. I tell the consumer, hi, here I have two contracts, this one, that one, different quantity with different payments. You select one of them, and then we make the deal. Otherwise, you have the option to do not do the business. You may choose nothing and then leave away. Okay? I may offer a menu of two contracts, the two first best contracts. Okay? In this case, the problem is that you cannot expect the type I consumer to select QITI, or I should say, you cannot expect different consumers to select different contracts because both of them will select the contract that is intended for the low type consumer. Okay? The reason is that by choosing this, they can earn more money. So in particular, let's look at the type H situation. He is going to earn a positive rent. We know its utilities like this. If he choose the low type first best contract, then his type is still theta H, but the quantity and the price are QLTL tilt, and then we know TL tilt is theta L times VQL tilt, right? And that's how you will get simplification like this, and because theta H is higher than theta L, type H consumer earns a positive rent by choosing the contract intended for the low type consumer. Or we can say, if we offer the first best, the menu of first best contracts, then both of them will choose this one, and you are not able to use the one for the high type consumer to extract surplus. So because you leave some rent to the high type consumer, now it's a question that whether this first best solution is optimal under information asymmetry, and indeed it's not. You may verify it, okay? But here, the key is that the first best option will not be implementable. Yeah, it's impossible for you to force or to induce the two types of consumers to select the two first best contracts. So this is because the first best menu, this guy, is incentive incompatible. Okay, this is our turn. By saying the menu is incentive incompatible, we mean that the type H consumer has an incentive to hide his type, to make its type hidden, and pretend to be a type L consumer. This fits our common intuition. Essentially, this sentence is saying that if my valuation is high, I'm going to pretend myself to be a low valuation consumer. If I feel I want to pay $100, I will try to convince you that I only want to pay $20 at most. Okay? Type H consumer has the incentive to hide its type. So that's why he is not going to choose the contract intended for a high valuation consumer. On the other hand, a menu is called incentive compatible if different types of consumers select different contracts. In this case, we say the contract induces truth telling. Why? If I offer you two options, and I know you are one of the two possibilities, if different valuation consumers will make different choices, then according to your choice, I can tell who you are, right? This is why we say incentive compatible contracts induces truth telling. So, if we want to get truth telling, how may we make my menu incentive compatible? Let's answer this question first. So, suppose I want to make my menu incentive compatible. In a menu, I still have two contracts. One is QLTL, the other one is QHTH. I allow the agent or the consumer to select one of them. In this case, I want the type H consumer select QHTH, and that means I need to have this constraint onto my four decision variables. The type H consumer will get the left-hand side when he selects QHTH. If instead he chooses QLTL, then the quantity and the price will become QLTL, and the right-hand side is his utility by choosing QLTL. I want type H consumer select QHTH, so I want the left-hand side to be greater than or equal to the right-hand side. I need to make sure that the QHTH contract is more valuable to the type H consumer or more profitable. Okay, this term should be capital TH. Okay, this should be capital TL. So similarly, for a type L consumer, I want to make sure that the type L guy will choose QLTL, and that just tells us that he needs to earn more by choosing QLTL. Choosing QLTL generates a higher rent to him than choosing QHTH. These two constraints are called incentive compatibility constraints, or IC constraints, or because they induce truth telling, we call them truth telling constraints. If the seller somehow wants to do business with both types, okay, then we need something more. We need the so-called individual rationality constraints, or IR constraints. Or because this is to induce the consumers to participate, this is the participation constraint. This is saying that for each type of consumer, the utility of choosing the intended contract must be non-negative. Okay, this is why he wants to do business with you. Here, these are typos. This should be I, and I. Okay. So the seller may offer an incentive compatible menu. Yeah, indeed, that's definitely some kind of options. But now our question is this really profitable, or is it optimal? Okay, I still impose some restrictions on my contract. Is it optimal? I don't know. Okay, that's the issue here. So we want to find the optimal pricing, the one that really maximizes my surplus, my producer surplus, or my profit. Okay, so in general, we want to determine a pricing scheme. Okay, that means a function T of Q that maps the quantity to a price. Okay, some examples are here. So for example, you may use linear pricing. In this case, you determine something like a wholesale price, and for each unit, the consumer needs to pay you P dollars. Or if you draw a graph, it would be something like this. Your price, T of Q, is a linear function of Q. Okay, that's one possibility. Another possibility is for you to adapt a single two-part tariff. Okay, in this case, you decide two numbers P and Z. P is the unit cost, and Z is the total cost, some lump sum fee. Okay, in this case, your function would be something like this. This is your Z, and T of Q is a fixed payment plus some linear payment. Okay, that's another option. And the menu we just mentioned, okay, these two contract menu can be implemented again as this general function. You just need to say, okay, if you choose these two quantities, you have these respective payments. And if you choose anything else, you're going to pay me infinity. Or somehow that just means I don't want to sell you any quantity other than these two quantities. If you want to draw a figure, it will be something like this. This is QL, this is QH, this is TL, this is TH. You have 2 points here. Okay, this is QL, QH, TL, TH, and then infinity, or a very large price for other quantities. Okay, so you know, in general, you are allowed to implement any menu, a menu with any number of contracts, if you just want to write down a general function. So all of them are some restrictions on my pricing schemes, and for each restricted contract format, we may formulate a problem and solve it. Okay, that's possible. And actually, I hope you will try to do that in your in home. But the question is, even if we do that, we cannot guarantee any of them to be optimal, right? Because we did not investigate other pricing schemes. How do you know the optimal pricing is not a square function? How do you know the optimal pricing is not a quantity discount? How do you know it's not sum log function, exponential function, whatever? In general, there are too many possible formats for you to investigate. Okay, so here, let's consider the most general pricing problem. In this case, the decision variable would be that function. The function of quantity T of Q means pay me T of Q when you order Q units. This is actually a menu of infinite number of contracts. By being offered this function, the type I consumer will think in the following way. He needs to somehow find a way to maximize his utility. Okay, his utility is like this. Now Q is his option. He can choose 2 by paying T of Q. So his purchasing quantity Qi hat, let's call it Qi hat, will satisfy this this relationship. It must somehow maximize his utility. Okay? Given a different T function, he is going to choose a different Qi hat. And my problem is to choose a T function that induce him to choose a particular quantity that can maximize my profit. Okay, and also I need to make sure that the consumer will really buy something, and I need to impose this participation constraint. So with this response, I know I will induce them to do these two things. Okay, the type L consumer is going to find one optimal quantity. The type H consumer is going to find another quantity, and this will be my expected profit. One interesting observation here is that even though you offered infinitely many options, eventually only 2 options will be chosen by the consumers, right? Because each of them wants to maximize their utility. So each of them will eventually fix to one contract or one option. Okay, this will happen no matter how many options you offer. They will only choose 1 or 2 options, at most 2 options. Okay, so that means offering infinitely many contracts is somehow useless, right? All you need to offer is just 2 options. That somehow simplifies the problem, but we need something more. So if we ignore what I just mentioned, the complete formulation is like this. I am deciding a function to maximize my expected profit, subject to the incentive compatibility constraint, each consumer will do whatever they like, and I need to make sure at the optimal situation they can earn some money. Okay, this is my complete formulation. And certainly a formulation is good, but how do we solve it? As we mentioned, it's almost impossible because there are too many possible functions. And here, we're going to rely on this one of the most important theorem in the whole field of mechanism design or information economics, the revelation principle, to greatly reduce the search space of our pricing plans. So we know there are a lot of possible pricing schemes or mechanisms, and some are incentive compatible, some are not. For example, if you offer a single contract, that's not. Or if you offer the first best menu, it's also not. Because in these two cases, the two different consumers will make the same action or the same decision. They will choose either just this contract, or they will choose one contract between the two contracts. Okay? You cannot tell or identify their types by their actions. But if you offer an incentive compatible menu, then you are able to do that. So at least you have two possibilities. The revelation principle tells us this thing. Among all incentive compatible mechanisms, at least one of them is optimal. Oh, so that's a very significant, very strong result. If this is true, we can ignore all those incentive incompatible contracts. That's not going to be optimal. Oh, sorry. Some of them may be optimal, but I don't care. Because in the smaller set of incentive compatible contracts, one of them is optimal. If I want to find the optimal contract or optimal mechanism, I only need to worry about incentive compatible menus. Among all these menus, I only need to find one of them. Okay? The problem then becomes tractable. The revelation principle is not founded by just one scholar, and at least these three scholars, Mirrlees, Masking, and Mearson, they put significant contributions to revelation principle, and eventually all of them got the Nobel Prize in economics. Okay, so indeed, their finding, the revelation principle and something else, okay, really help us to advance our knowledge regarding information asymmetry. And it's actually because we have revelation principle, because of their contributions, that we can really do any analysis. Okay, so certainly there are other contributors, and we cannot list all of them. All those work are published around 1970s to 1980s, and after 20 or 30 years, eventually they got the Nobel Prize. Okay, anyway, so we have revelation principle. If we do not care about anything, we can go back to solve the problem because we have a very powerful tool. But before that, let's briefly discuss why revelation principle can be true intuitively. So in general, the revelation principle is saying that we want to design a mechanism for the agents, and the mechanism somehow means a game rule. Agents will act according to these rules. Okay, I want to use the principle to help me design mechanisms. So before that, let's categorize mechanisms. When an agent has a private type, at least there are two kinds of mechanisms. One is called indirect mechanism. In this case, you specify game rules as follows. I say there is a function mapping your actions to payoffs. For example, you choose your quantity to order, and then I tell you how much it is. Okay, this is a function mapping actions to payoffs. Each agent, suppose there are a lot, based on his type and his belief on other agents' type, acts to maximize his utility, his expected utility. I'm sorry, this should be utility. Okay, and also here the sentence is written down for the multi-agent case. But if you don't want such a complicated situation, think about one principle in one agent. This is nothing but each agent will choose his action according to his type. Just as if you have a low valuation or high valuation, you will based on your valuation to make your ordering decision. Okay, that's something happens in indirect mechanism. Another thing is called direct mechanism. This is something very interesting. So the principle is going to specify a function mapping agents' reported types to actions and payoffs. Okay, what does that mean? I ask the agents not to choose an action. Instead, I want them to report a type. No one says they're going to report their true types, but I'm going to specify a function that's going to assign actions and payoffs to agents according to their type. Okay? Each agent will, again, based on their types, report a type and try to maximize its expected utilities. Okay? This is the situation. So here, under a direct mechanism, what's happening is that, for example, in our previous case, you tell me your valuation, low or high, and then I will give you a quantity and a payment, or I will charge you a price. Okay? That's exactly, I give you two options, QHTH and QLTL. And then you select one of them, right? What we mentioned about direct mechanism is you report a type. I give you a quantity and price. Or I give you two quantity price pairs, you select one of them. Essentially, that's the same. The only thing you need to care about is whether they really report a true type. So if a direct mechanism can reveal agents' types, that means making them report truthfully. Then it's a direct revelation mechanism. Okay, so here we have indirect mechanism, direct mechanism, and a direct revelation mechanism. The principle is like this, is saying the following. Given any equilibrium of any given indirect mechanism. Okay, so now there is an indirect mechanism. There is always a direct revelation mechanism in which the equilibrium is equivalent to the given one. Moreover, that just means the agents will do the same thing in these two equilibria. Okay? So, I give you a contract or a mechanism. Okay, the agent do some response. I can always find a direct revelation mechanism that can replicate what you have just done. Okay? So that's exactly telling us direct revelation mechanism, one of them will be optimal. So how may we show this is true? The idea is to imitate the given equilibrium. Because now I am saying you give me your type. I assign you an action and a payment. So I can somehow assign you actions. So let's see how may we do this. You have a given equilibrium. Okay, this equilibrium specifies each agent's strategy to map his type to an action and his expected payoff. Right? Somehow there is an equilibrium. Somehow each agent play the game and find their strategy and payoffs. We may construct the direct revelation mechanism as follows. So given a type report, true or false, I don't care. Given a report, I first find the corresponding actions and payoffs in the given equilibrium, in the original equilibrium, as if they are really of those types. And then I assign exactly those actions and payoffs to agents. So what does that mean? I know the original indirect mechanism eventually results in something, results in an equilibrium. Now I construct a direct revelation mechanism. You tell me the type. Okay, that's okay. Sorry, I should say you construct a direct mechanism like this. You give me your type. And then, according to what you should do in the original indirect mechanism, I assign you those tasks and then give you those payments. Okay, that's what I mean for imitating the given equilibrium. If I really do so, then the following thing will be true. Suppose all of them report truthfully under the direct mechanism, then what they will do and what they will receive will be exactly what happened in the given equilibrium, right? And moreover, because this is an equilibrium, no one wants to deviate, right? So in this direct mechanism, no one will lie, because once he lies, he is going to be assigned different tasks and different payoffs. That's going to be a deviation in the original equilibrium, and that's not going to be good, right? Because originally no one wants to deviate. So that's the intuition for the revelation principle. Certainly, if we want to prove it, we need very complicated notations, but let's forget it. So eventually, this provides us a guideline. If you are designing a mechanism, if you are designing a contract, you need to find the agent's type. You need to screen the agent's type through your contract, through your mechanism. That's going to be the optimal thing you need to do. Okay, so we have the revelation principle. Now we know we only need to search among menus that can induce truth-telling. That's the first thing. And different types of consumers should select different contracts. So because there are only two consumers, so we only need two contracts. So this is very interesting. If we offer only one contract, that's too few. But if we offer three contracts, that's too much, too many. We only need two contracts. That's optimal. So the problem we need to solve has four decision variables. We need to design two contracts. Each contract is a QT pair. Okay? And then we need to have incentive compatibility constraints. We need to have individual rationality constraints. This has all been discussed to be constructed in the beginning of this lecture. Okay, SE constraints ensures truth-telling, IR constraints ensures participation. Now we know this is the problem to solve. This will give us the optimal pricing plan. Now let's introduce how to solve this problem in the next video.